Is it okay? I believe so. I believe so. Is the thing moving? Yeah, okay, perfect. Okay, let's start. Sorry for the delay. Okay, first we start with the definition of the LDMBC. Okay, it stands for linear. It stands for measurement-based computation with ZD linear classical processing. So linear over ZD and measurement-based computations. Okay, so in this setting, we have some classical inputs, which I equals some I1 up to some IN, which is ZDN. Okay, and the output we denote by OI would be something in ZD. And then let's assume we have n parties. And the idea is each parties will receive an input we label QK from a classical control computers. Okay, parties have received an input, and then we'll have an output denoted by SK. Okay, so K is something between n parties, such that first things, it satisfies Q equal TS plus QI. Okay, so when I say S, which means order, Sn, and I is basically the string. Okay, so T should have dimension of, right, T. And Q should have dimension of n and small n. Yeah, so it's just a relation between what the particle received in terms of the input I and certain outcomes. And second thing, for suitable ordering of the particles, okay, the matrix T is a lower triangular matrix. With diagonal 0. Okay. Yeah, so as I said, by ordering the party in a nice way, then this T will be a lower diagonal matrix. So for example, the second, the Q2 can be depend on the outcome for the first particles and certain relation for the I's input. Okay. Okay. The final thing is the output. Output I should be some linear combination of the output S plus a constant mod D. Okay, so after every particle output some Si, then the computational output of the whole scheme is some linear combination of the S. Okay, that's exact. Yeah. Okay, and that's a thing. If T is a zero matrix, then the whole scheme is called temporary flat. What does temporally flat mean is basically the Q does not depend on the outcomes of each particles. Got it? Because this is 0, then the Q only depends on the input I. That's what it means. Okay. And in this talk, I think I'm focusing on temporally flat. Okay, next. Next, what we want to introduce is the whole point of the talk is the linear over set-mod declassical computing of quantum measurement-based computations. Okay, definitions. Now it's a more specific setting, more restrictive setting than that. We have the MBQC and it's temporally flat. I kind of try to rewrite the definition in a more convenient way for the talk afterwards. Okay, so now we will in MBQC, yeah, we will involve some quantum state in the definition. Now in here we only say we have certain particles, we don't know what's going on, or the quantum thing will happen within the particle, but we don't have any information in that settings. And now we'll throw in some quantum behavior in some sense. Okay, again we have the input, say I1 up to IN. And again we have the output. Now we need to have a resource state. Any state in D-dimensional, and depend on how many party you have, then you raise it to certain powers. Okay. The first thing is the Q, the measurement setting Q now is do not depends on S, it only depend on I. So we'll write it as measurement setting QK would be some function of I. So Fk should be some set Dn to set the linear function. Because now the input Q is only depend on I, but nothing to do with the outcome S. That's the first thing. And the second thing, we have a restriction on the measurement settings. Okay. So we will input a QK into each qubits, and depend on the QK, we'll have an explicit measurement that we want to take, which I label by capital MK QK. Okay, we have this measurement. On each qubits such that MKQK is equals to UKQK. Okay, such that they're kind of related by an action of a unitary matrix. And in practice, normally we'll think of the Clifford groups, which I will explain later what Clifford group is, but basically they are all related by a unitary matrix in this sense. Okay. And the thing is, when you have a measurement, then you have some eigenvalue. You have some eigenvalue of this form. You have omega raised to certain power. So omega is 2 to the e pi I over d. Okay. And when you take this measurement, then the outcome of after you taking measurement will denote outcome denoted by small k. Denoted by small k. Okay. And the third thing is the outcomes. The outcomes is already in function. Yeah, because it's just linear combination of all the outputs, so you can just write it as just j from 1 to n sum alpha j m j or simply by mk, some mj plus certain constant. I mean mod d. This is what the output looks like. So certain linear combination of all the outputs here. Okay. Now, a diagram, I mean, kind of a picture to see what exactly is going on is, okay. We basically have a control classical computers which can only calculate certain linear functions. Okay, so first, we have an input in some n variable into that class control computers, and then we will execute a bunch of linear functions. So we have, say, we have n parties, or nq this. What I meant is, or nq this. Okay, so we'll, for example, we'll first execute f1, so it will have it will output a q1 to the first qubit, and then it will take the measurement m1, and then after taking the measurement m1, it will send back the information to a control computer with the output m not k but 1, and so you have n q this. So you have, last one is this, you have the qn, and you send back the mn, and then after that the control computer with all the information of m1 up to mn, and then he performs certain linear stuff, so the O, some linear stuff, and then you got your outcomes, the final computational outcomes. That is what the whole MBQC looks like. What's the measurement? So so we have a state on NQ this, and this is a setting we need to set up. So if you receive, say, QK is 1, then what measurement you want to take? That's a setting that we need to choose. Some polys.
It's kind of agnostic about the specific kind of measurement. I mean, they could be any sort of physical system that has a certain, so qubit stands for D outcomes. Say that you want 2 outcomes. It could be like an electron with spin up and down, or the polarization of a photon. But say you want 3 outcomes. You could think of perhaps some sort of atom that you excite from a ground state to a first excited state to a second excited state that are sufficiently separate that you can count these as 3 outcomes. Because when you do a measurement, you get some sort of photon that is emitted from the atom, so that you know that it was in this second state or this first state or the ground state or something. But for most of these in this field, generally we're kind of agnostic about the specific physical process. We just look for any 3 outcome system.
Very good. We have a physicist to explain some physical problems. Okay, now we are going to give examples on such a setting. Okay. As I remember, Simon have given 9 gates like a few weeks ago. Now we're doing a different gate. So it's an example. we pick our state to be this state root 2 0 0 0 plus 1 1 1. There's a name for it, but I don't know how to pronounce it, so I didn't write it. Yeah, exactly, but I don't know the full name, so okay. The aim is to output the OI. What we want to do is we want to execute the OR gate. Okay, now introduce some function matrix or Pauli matrix first. So X is this one, and Y is this one. Okay. In terms of the, I mean over set 2 in this case. So the 0 and 1 state in under the X operation, it will flip it, and Y would flip it with a phase change. Okay. Okay. Now, in the set, okay, in this case, we want to have 2 inputs because we're doing the OR gate, so we have 2 inputs, and we want to output the result of taking the OR gate. Okay. So the input is I1, I2, so set 2 to 2. Now we want to pick the QK or the measurement setting first. So Q1, I take it to be the I1, Q2 to be I2, Q3 to be I1 plus I2 mod 2. Okay, so basically it's the function fk. Okay, and then we need to pick the capital M. What exactly are we measuring over the qubits or qubits? If the qk is equals to 0 or 1, then the mk would be xk and yk. The subscript k here basically means which bit are we taking the which qubit are we taking the measurements. Okay. So we know what measurement are we going to take, and then the final output, we take the sum of all 3 of them, mod 2. Okay, that is all the setting that we have, and we want to verify whether it computes the OR gate in this sense. Okay, first, let's say I1 is equals I2 equals 0. In this case, we have Q1 is 0, Q2 is 0, and Q3 is 0. In this case, we have 3 parties. I mean, 3 qubits. So with 3 qubits. And then we want to measure the measurement is, so both of them are 0. So both of them take the X observables. So X1, X2, X3. And then what we want to observe is that if you take this, it will stabilize the state, because what X does is flipping the state. So if you have 0, 0, 0 and 1, 1, 1, after the X, you just flip everything, then it will become 1, 1, 1, 0, 0, 0. So it stabilizes the state. In this sense, then we know that, so we have X1, X2, X3 stabilize the state. Therefore, we know that M1 plus M2 plus M3 would be equals to, basically in this case, you have 0 mod 2, because it's basically omega 0, 0 mod 2. Okay, we can do another case. For example, we can do I1 is 0, I2 is 1. Okay, in this case, Q1 would be 0, Q2 would be 1, Q3 with sum of them, and then the measurement would be X, Y, and Y. Because Q1 is 1, then you take the Y measurement. If it's 0, you take X measurement. And now we want to observe this is equals to minus this. How do we do that? Is just observe what's the phase, because all x, y, z, all x and y will flip the state. So we know 0, 0, 0 will certainly map to something 1, 1, some state of 1, 1, 1. We just need to see what is the phase or constant here. Then if you apply a y, if you apply y to 0, you have an I factor. Since we have 2 qubits, so we have I squared, so it's minus 1. Yeah, that's how you observe it. And 1, 1, 1, of course, if it's go to 0, because you always flip it. And we want to check the constant by, we're applying, this one you don't count anything. But for these two, you apply by a y. And for each one, you will have a factor of minus I. So in here, you should have minus I to the squared, because you have 2 qubits which measured by y, and this is minus as well. So this one holds. And therefore, we have M1 plus M2 plus M3 will be 1 mod 2. Yeah. And for the rest, feel free to check it if you want. It's pretty, just like this. You just take other input. So I1 is 1, I2 is 0. Then you just do the same thing. It will stabilize the state either plus or minus. And then after checking, you'll see that it exactly executes the OR gate. So if you input this one, the output should be 1. If you input this one, your output should be 1 as well. Okay. So it can do something with the OR gate. Next. Okay. Okay. Let's say we want, okay. The idea is we want to know whether, because OR gate is not linear, and the thing is someone have found a relation between whether you can execute something linear and the relation between whether you can execute something linear to whether the whole system is contextual or not. Okay, for contextuality, if you want to have a detail, go to some previous talk. We have a kind of 2 or 3 talks about the strongly contextual or whatsoever. But I can give you a very short definition, which is pretty useful in this talk. Okay, so we have some measurement settings. So it's basically, yeah, I'll do an example. Okay, and we have a context, measurement context. Okay, the measurement context is this. M1Q1 equals F1I up to M and Qn equals Fni. So this is the measurement context, and you take the union. So because you have different input, you take the union is all the measurement that you want to have in your system. And that's the measurement context. It's basically this one. You just plug in I in all the qubit or qubits and see what you got. In this case, the measurement is XYY, xxx, etc. Okay. And then when we talk about strongly contextual, in this talk, we can just think of it that if it is not strongly contextual, then every measurement locally will have a predeterministic outcomes. What I mean is, if it is not strongly contextual, then when you measure the first qubits by this measurement, it will always have the same output. Okay, yeah, that's the only thing that we need to know. And then, okay, and then we can state the theorem. Okay, let's say a system is L2 MBQC, which deterministically evaluates a Boolean function. Okay, you have an MBQC. If the function that you evaluate is not a linear function, then the system is strongly contextual. Just like this. Okay, the proof is it's not that hard. Okay, remember what we said is, okay, let me write down the count of the, okay. The proof is not that hard. The idea is for every measurement, so you have MKQK is 0 and MKQK is 1. Since it's over set 2, we only have 2 choice of measurements. And since we'll prove the contrapositive way. So we're trying to prove not strongly contextual imply linear. Okay, so we assume it's not strongly contextual. It should be C. And then for every measurement that you take, you always have a fixed it will always have a fixed outcomes. That's what the definition said. And then you can form it into an equation, CK, SK, CK, DK. Because you are taking the QK either 0 or 1, then you will output like SK. Because this is fixed, then you can express it into linear equations as follows. Okay. And then we have, say, n parties. Then you can form S1 is C1 plus D1 Q1 up to Sn equals Cn plus Dn Qn. So we will have a bunch of equations which relate the outcomes and the measurement setting inputs. Okay. And then if you consider the whole thing as a whole factor, then what you got is you have S equals C plus DQ. Right? You just put everything into a vector form. And then by the definition that we got, we have, by the way, this is not just for temporary flat, it just stands for all the MBQC, not just temporary flat. We have Q equals TS plus QI. Remember the definition, the setting input is depend on the outcomes and the classical inputs. Then you just plug everything in. So you will have this in there. So you have C plus D, TS plus QI. And then you try to simplify it. then what you got is I plus dt, multiply, put it on the other side, take the s out, and c plus dqi. Okay? And then, okay, first, this D will be a diagonal matrix because this is a constant, you're taking diagonal matrix. This one is a lower triangular with 0 on the diagonals. And when you add the identity, and the determinant will be non-zero, right? You always have the diagonals, lower triangular with the diagonals 1. In this sense, this matrix is invertible. So what you can do is you can definitely solve for x. You can solve for s. So if you have c plus dqi with certain inverse, you can solve for s. Now, if you can solve for s, which means this one will be linear because you're applying linear on some fixed value plus a constant, it will still be linear. So we'll prove that if it's not strongly contextual, every measurement will have a fixed outcomes, then you can form a set of equations and you just mess around with the equation and you can solve for the outcomes. And therefore the computational output will be linear. And that's how we prove that theorem. Okay. Halfway through. The idea of the whole talk is whether it's contextual and whether the output will be linear, they have relation only in L2 case. If you go to set mod D, then the relation doesn't really hold. So we're going to explain that. Okay. Okay. First, what we want to do is we want to know whether the set D MBQC can actually calculate something nonlinear first, right? If it can only calculate linear, it doesn't make any sense to have a statement like that. Okay. But first, we need to know what's Clifford groups, because that's the main object that you can construct nonlinear stuff. Okay. The idea is what's Clifford groups. Okay, first, what is Pauli groups? Pauli groups, I'll denote over set D. Is generated by n-fold tensor of element of forms x, z, and omega. I mean, this non-two, or this odd prime. Let's make it easier. This odd prime. Okay, first, omega is the deep root unity, and what the x does is do this. I mean, mod D, of course. So if you have D minus 1 here, you map to the 0 state. It's mod D. And the set is it will not change the state, but it will raise to some power of the omega. That's called the generalized Pauli matrix. So the generalized Pauli groups is generated by, so you have n-fold tensor of those. So you have x, tensor x, or maybe tensor z, and tensor something x, z, something along those lines. So you have a bunch of tensor of these combinations. And that's the Pauli groups. Okay. And then, in terms of calculation, sometimes it's easier to represent the Pauli into something called a while operators. Okay, this operator is as follows. So we denote by a capital W with some subscript where V is A, B inside set D to 2n. I mean, in this case, n here 2n. Oh, that's true. 2n. So each of them is in set D to the n. Okay. And then we define, okay. So something like that. And what it does is defined as taking n-fold tensor of something smaller. So this is equals to minus AI BI set AI XBI. Okay. So for each AI BI in set D, so for every element in set D, you have these expressions. So it's kind of like the general Pauli. That's X and Z is the Pauli. Okay. And the n, so in this case, say you have 0, 0, 1, 1. So what it does is, this one is the A1 and A2. This one is the B1 and B2. So you have something along, you won't have any power on the set, but you have power on the X. So you have something along X, tensor X, with some phase. Okay. That is the wild groups. It's just a nice presentation so you can work on the Clifford group easier. Okay, now definition of Clifford groups is as follows. The Clifford group we denote by that. It is some subgroup or some subset of the unitary of set D, some n tensor of some unitary group over complex to D power. Okay. Okay, and the definition is as follows. Some unitary matrix such that there is inside the Pauli for all P in Pauli. Yeah, so it's basically all the unitary matrix such that you conjugate every Pauli by that unitary, you still got some Paulis. That's what the Clifford group means. Okay. And then, and if you have a Clifford groups, then you can decompose it in some sense. You can factors it into, so I still use the V, you can factor into some U, okay. You can factor into some while operators or some Paulis and some unitary, which is some octomorphism on the set of while operators. Okay, what I mean is, if you add this on some Pauli operators, what it does is you do some linear transformation of that vector. So it will equals to some W to some something. I think I do set D, right? Yeah, the dimension. Yeah. So when you do the action on a Pauli, it will basically have some linear operation on that vector. And we want to denote that thing by C and the U to V. Okay. these things is called the symplectic part of the Clifford groups. So, okay, so when you look at the Clifford group, what it means is this one is basically control what poly does it act on. So it's control the plus or minus sign. And this one will control which poly does it go to, because it will change the poly to, say, X, you can go to Z. But yeah, that's the whole thing. Okay, so you can factorize the Clifford in this way. And then we have something called the symplectic inner product. Is as follows. So you have some factors 0, -1, 1, 0, W. Okay. It's just a inner product, a special kind of linear product. It's called symplectic. And the good thing about this is we can compute the commutation relation of the while operator easily in the following sense. Maybe I should not use W. Let's say Z. Okay. Okay. This is useful because we have this relation. Feel free to check it if you want, but we have this relation. When you commute them or flip them, you'll add a phrase to it. That's why that's useful. Yep. Yeah, that's the whole Clifford group story in a brief sense. Okay. And then we want to have an example on how the MBQC over Z mod, not 2, but Z mod D, which can calculate something nonlinear in the following sense. Okay. We pick our state to be this one. 1 over Z mod D. Sum Q plus D minus 1 tensor 2. Okay, we pick the state and we need to pick all the fk function, remember? And then we pick the fk to be the same function. We don't care about which k are we talking about. We just take all the k to be the same function. And then maybe one more thing here. I don't think you're very keen on rework out all the details, so maybe I just gave you this one. If you have some Pauli's, no, I mean Clifford. What notation do I use? If I have some Clifford groups, maybe I write properly. Okay. Just hang on for a second. We need a formula. If we have a Clifford groups, and that's a relation that we want to have. Okay. Remember that when we talk about the definition of MBQC, the measurement setting will differ by a conjugation action of the Cliffords or some unitary, but normally we take the unitary as Clifford. So we want to calculate what this looks like. And remember, we can factorize it over that. And that we can also factorize it. Okay. And then the computation get a bit messy, but the whole idea is you keep on pushing this U to this side. So you have U, X, U. Okay, I do first filter. Okay, what we want to do is we want to move. Let's see what I want to do. Yep. I want to move this U to this side, or the U to this side. by applying, maybe I didn't write it. Right, no, we did. By applying these things. Actually, this is not there, this -1. Sorry. Yeah, by applying these things. So, for example, when you move this u to other side, you have w, ux, and then u, wx. And then you need to move 2u to the other side. And then what you got is, you move 2u on the other side, and x, and you have 3u and then wx, etc. Then feel free to work it out, but yeah, this is not the point. The point is, after you do such a thing, then you can get a pretty nice formula. You have some omega, the sum of k is 0, f by -1, the symplectic, k here, with the while operation, v. Okay, yeah, once you move all the u there, and then you'll get some equation like this. This term is basically these terms. So yeah, it's pretty awful if you write everything out, so trust me on that for a second. Okay, that's the formula that we want to have. And then we can go back to the example. Okay, we have picked our f function, and then we want to pick, the v here to be the phase gate. So let's say v is the phase gate, which is, if you do it in terms of matrix, is 1, 0, 0, I. Okay. And then the good thing is you have this relation. Minus k is equals to tau minus k zkx, where tau square is omega. Yeah. Feel free to check. It's just pure matrix computation, and you can check it. Okay. And then what we want to check is this one. We want to check this thing can stabilize the state. These things, remember, is basically you conjugate it by the phase gate several times. So basically it's this one. But you do this one on all the qubits, or all the qubits on this state. So you have skx s minus k on, I do it just for one qubit, and you'll see what's going on. I do it on q, just random q. So you have this form, tau minus k zk x on q. When you do the x, you add it by 1. And you do it by z. Have I erased it? No. When you do it by z, you have multiplied by the state by a phase of omega to the power of, you multiply the state by the phase to omega q plus 1. But you did k times, so you might multiply by k here. Okay. This is just for one qubit. And the thing is, in our state, we have 2n qubits. So you raise, so if you have 0, 0, 1, 1, 2, 2, let's say, then everything will plus 1, plus a certain constant here. But we have 2n copies of such a constant. So you raise everything by 2d. Right? And then the tau to squared is omega. So we have something omega minus omega, wait, I'm canceling. Okay, omega kd and omega d to something. But the thing is, omega d is 1. Because I take the d unity root, the d root. So it will goes to 1, 1, 2, 2, 0, 0. You see how it stabilizes the state. Basically, you add everything by 1, and the scalar will be 1 because every qubit you have some constant, but you raise by multiple time of the qubits, the constant will be 1. Therefore, we can stabilize the state, and we have such an equation. So we have these things, Fi to V to the state is equal to the state. Okay, we have these relations. Okay, so maybe let me erase this so that I can do it in the same board. Okay, so when you do the measurement on this whole thing onto the state, the outcome will be depends on what this is, because this stabilizes the state, so we only have this constant left. So what we have is the outcomes would be the sum k equals 0, Fi minus 1 x c kv. Okay. Since we picking, basically we pick this to be the x operations. Okay, if you do some computation, these things will exactly equals k. So what you have is you sum up to k, and then you just sum it up in a normal sense. Then f is linear functions. So what we showed is you can compute something in quadratic or power 2 functions. Yeah, because two linear multiplied together is quadratic. So it's possible to calculate something nonlinear first. That's what this example want to show. And then lastly, we want to prove some theorem that put the relation on whether it's contextual or not, and whether you can calculate something nonlinear.
Sorry, this was for arbitrary D, or this example, did you specify D? Sorry, maybe I missed.
Actually, I think arbitrary T would work, but I think the whole idea is we can do the whole MBQC for some nonlinear thing, even D is not true.
Yeah, so I had a question about that.
Yeah.
So we did a paper a couple of weeks back by this guy Hobang, and so the basic idea was once you go to Zmod 2, when you have a local function Z2 to Z2, it's always linear.
Exactly.
And then ZD to
ZD to ZD is not linear.
ZD is not always.
Yeah, that's
linear.
the whole.
That's the basic idea.
Yeah.
Right?
So why the whole thing doesn't work when you go over Z mod 2? Yeah. Okay. Now we go very quick. Okay. Okay, just last few words. Some definition first. Some definitions. Okay. I still don't know why Marcus and them use this notation, but it's the polynomial rings on n variables. Okay. You roughly know what polynomial ring is, right? Is that okay? Oh, so basically it's some polynomials of this form. So f is a polynomial, and we take n variables, so x1 up to xn, and we have some constant, and x1 to some power, x2 to some power, up to xn to some power, maybe I. Yeah, just a bunch of combination of Z1 up to Zn, and the coefficient is in Z mod D. Yeah.
a function. You can
Yeah.
think as a variable function.
That's
Like, yeah, you can think as
Many variable
many variable function.
but restricted just to
Some
finite terms, right? Polynomials. Can it be? Is it infinite there?
No, you can't be infinite because we take it to set mod d. The highest power is d. I mean d minus
Exactly,
1.
that's what I was
Yep.
get to. Yeah.
Okay, so we have a kind of general bunch of function, and we have a term. Normally L is stand for linear, so what we have is we have some linear function, also basically some element inside here, such that you take L, x1 up to xn, let's say, is equal to some c0 plus j equals 1 and cjxj. Yeah, so some linear function with, so every term have order 1 or degree 1. Okay, last things is omega n to delta. It's basically, okay, aj. So okay, so first aj is inside the field, and the sum of aj is less than delta. It's generated by those. Okay, so briefly is you have a polynomials and the degree is less than delta because we're taking sum of all the, yeah, that's how you define degree of a multiple variable polynomials, just taking the orders of it. Okay, this is the definition that we need. Okay, and we have some theorems, some pretty general theorem not related to quantum, but general theorem about some functions is for every function g from set mod d to set d, I will exist some polynomials inside here such that partial degree is less than d minus 1 in all variables, and fx is equals gx for all x in, yeah, I don't know how to explain. So the basic idea is given any function from set d to set dn to set d, so an arbitrary function, any function that you want to put, this theorem said that you can always express that function in terms of polynomials. Okay. For person who curious of the proof is you use a delta function. So you have delta, it's just, okay, so that's the standard delta function. And the thing is, you can express your function g as follows. You can sum it up with this one. Yeah, you just break down your function into a bunch of sum of delta functions. And the thing is, actually, the delta function can be expressed as this. Yeah, that's the whole idea of the proof. You express the delta function in some polynomial of partial degree less than d minus 1. And then you express your arbitrary g into the linear combination of those. Then that's why the outcome will be some linear combination of some polynomial or partial degree less than d minus 1. It's just a random proof. Okay. And then we have one more lemma. Okay. One more lemma is let G is inside some omega 1D. So it's basically a polynomials. So in one variables. Okay. And degree of it, let's say is delta. Then we have the following. L1 FD Gn composed with L. Okay, so what we do is we apply some linear function in n variables, and then we apply some polynomials, and then we apply linear function. The outcome would be some function of this form. The idea is as follows. When we draw the diagram, it will be much clearer. Okay. We'll see how these things work. Okay. This is two results that we need to state the final theorem. This is the final theorem. Okay. M be a linear over set mod D MBQC, which is temporally flat. So it deterministic evaluate a function. So I have a MBQC, temporary flat, which calculate a random function. Okay, now if the output, by that theorem, you know that every function can be written in certain form of polynomials. So if the output involve at least one term of forms j equals 1 to n xj aj, such that sum of aj is larger than d, then M is strongly contextual. Okay. We want to prove that in an easy way. Okay, so basically, your output function is an arbitrary function, and by that theorem, we know it's a polynomial. So this theorem says if your polynomial have some terms have degree larger than d, and then M will be strongly contextual. How do we prove it is as follows. So again, we suppose it's not strongly contextual. Strongly contextual. So which means every measurement input, you always have a deterministic fixed outcomes. So what we have, okay. Remember we have the huge control computers, and we have I. So first we apply some linear function to get the Q, right? So we apply some linear function on n variables. Okay, I just erase this square, this not useful. Okay. You have an input, and then we can get a Q1 because the Q1 is depend on all the i's. So we apply a linear function to get Q1, and then we do the quantum measurements, which we know we have a fixed value, but we don't know what it is. So let's say we have a G1, so it takes some D to D. Okay, and then so we have input, and we have the fixed measurement outputs M1, and then we apply some linear function on one input to some M1 plus C1. Is that okay? It's more like the whole thing. Okay, we have n parties, so we have a lot of, so now we have Qn, and we have Mn, and we can alpha Mn n plus Cn. So we have Gn here with L1 Fd here. Okay, this if you have non-contextual, which means this is a fixed outcome. So you always have a function to do such a thing. Okay, now function from D to D. By that theorem, we know that the degree need to be less than D. I mean, the degree. Okay, let's first consider this side, this part. By the theorem, we know that the degree of maybe not I, some G will be less than or equals to D minus 1, right? Right? Yeah. Yep, D minus 1. Okay. And then by the lemma, we know that all this part up to here. So we first apply these things and we apply a polynomial of degree less than D minus 1, and then we apply the L1. So just consider the first ring. Up to here, we should have something inside omega n Fd delta, right? Okay. So what does that mean is you have polynomials with with the degree less than. So yeah, you have a polynomial with degree less than delta. Not delta. I mean D minus 1. Yeah. And then the computational output will be the sum of them. Alpha n, mn plus cn. So every row here is a function which is a polynomial of degree less than D minus 1. And for the computational output, we are basically taking the sum of them. So if you sum a bunch of polynomial of degree less than n minus 1, the degree will still be n minus 1, right? Because you're just adding them up. Which means this function would be inside here. Which means this is a function where the degree is every term have degree less than or equal to D minus 1, which exactly the negation of this statement, right? Because there's at least one term degree bigger than D, and he say that every degree less than D minus 1. So that's how we prove the whole things. Yep. Yeah, and we finished the talk. Yeah, so basically we have shown that linear condition does not work nicely in terms of contextuality. The relation is not that nice if you go D to some odd prime. Okay, cool.
Good, because your phone did something. It flipped on and off, and now it's and now the picture is the wrong way.
I see.
Yeah.
That's weird.
Yeah, I don't know.
I don't know why.